Yeah, so this is a thing about which dogs are faster. My claim is you guys know a bunch of functions, and I just want to talk about which ones get big fastest. But some of this basically amounts to I just want to spend a second talking about a misunderstanding that a bunch of people usually get through pre-calculus. So if you think you understand everything about pre-calculus, look up here quick. Question is, which is bigger, x to the fourth or x to the seventh?
Without knowing the variable of x, they can both be the same.
Or they could be less.
Yeah, good. Right? These two objects are not actually comparable. This question doesn't make any sense.
Yeah.
Why does this question not make any sense?
Because there are a lot of things left out.
Like you could have a negative number or fraction.
Yeah, specifically, I didn't tell you anything about where x lives, right?
Could be bigger than the other. You could have an imaginary. You could have a complex number.
Okay, so let's leave the complex numbers out of this discussion at least. But, and heck, we'll even leave the positive numbers out for a second.
Okay. Negative.
Or sorry, the negative numbers out for a second.
Oh, okay.
These are the positive ones.
And then, so if your x value is, like, say, just if it was 1, then your x value would be 1 for both of them. Therefore, no matter how big the number gets, it's always the same. So 7 will always be bigger. You know what I mean? Because it's x. X equals, and both of them have an x. So if the x is 2, then both of them have to be 2. Therefore, 7 will always win.
But what if you're like a, what if you're like 1/2?
Oh, if you're low. That makes sense.
Yeah, so if your x is bigger than 1, strictly, then Bailey's right. X to the 7th is always bigger. Right?
Then if you start getting low.
If the x is actually equal to 1, then they're the same size, right? So over here, x is 1 is kind of an interesting spot, right?
Yeah.
That's right here. Both of them go through 1.
And then what about 0, 0?
Nice.
They're both the same there as well.
So, blue thing,
Not red.
red thing. Just trust me, it'll be fun. It'll be fun, don't worry. Blue thing, red thing. I'm going to make the red one x to the 7th, and the blue one x to the 4th. Okay, so they both go through the points 0, 0, and 1, 1. Right? Okay. Then, let's see. In between there, okay, so let me think about a half, right? So at a half, x to the 4th is I just got 3 different powers of 2. That would be 2 to the 4th, which is a 16. So that's down here someplace, right? That's a 16.
So 16 of those will get up to your 1. That's fine. Not down scale.
Yeah, so that's too big, right?
Yeah, that's good.
And this next one's going to be even way
1
too big.
over 128.
1 over 128 is way down here someplace, right? Okay, so in between 0 and 1, it seems like the blue one is bigger, right?
Yeah.
Oh, that was really crap drawing. Really crap drawing. Don't.
Too late.
Shouldn't be forgiven for that kind of
Alright,
trash.
forgive them.
So,
Don't take
on the other side,
the switches.
it switches
Drastic.
drastically. That's good with that?
Yeah.
On the negative side,
Well, it's, you have like even and you have odds.
yeah, there's some cases, right? So if they were both even powers, they'd both be kind of parabolas pointed up, right? Like, not actually parabolas, but like parabola looking. You guys with me on that?
Yeah.
But since one of these is an odd power, the x to the 7th goes down, and the x to the 4th goes
Up.
back up.
So, unless, of course, you shift it by any thing with a lesser exponent, it will be less jumpy stuff.
Yeah, so we could, yeah. If these were polynomials of 4th degree and 7th degree, then we would have a much harder time answering this question. You guys kind of good with this?
Yeah.
So, at least on the right-hand side, the higher the degree is, the bigger it is after 1 and the smaller it is before 1.
Yeah.
You guys with me on that? Okay, so now let me ask about a weird one. What about x to the 1/2 power?
So square root.
Yeah, so the square root.
Okay.
Yeah, well, like,
Yeah.
It would just flip.
Okay, so the square root is x squared, right? Flipped over y equals x. So that's going to look like, is it going to go through 0, 0? Square root of 0?
No.
What's the square root of 0?
0.
0.
Oh.
I'm going to have a whole stack of colors here by the end of this. And does it go through 1, 1?
Yeah.
Square root of 1? Pretty sure it's 1.
0 to the power of 1. Oh no, it's, yeah, 1 to the power of
1 to the 1/2 power.
Yeah.
Okay. And in here,
that's
1 over this.
1/4. No. That's not right.
square root of 1/2.
Yeah, so I'm wondering, what's this?
1 over square root of 2, which is
Yeah, whatever 1 over
a
square root of 2
little
is.
bit smaller than, with a
Root two over two.
little bit.
It's definitely bigger than 1.
Okay, so hang on. So I'm supposed to be doing, I'm like thinking about 1 over the square root of 2, right?
Yeah.
Be rational.
Okay, and then if you rationalize it, you get square root of 2 over 2.
Yeah.
And this is like 1.4,
So high, so less than 1.
so definitely smaller than
Yeah,
1.
Definitely smaller.
But, yeah, so right.
But also bigger than a half.
Yeah.
Bigger than a half,
You gotta
right?
be.
Because it's like 0.7. Okay, so that goes up here someplace. You guys see that? So that's this guy.
Wow.
Okay. And then one more. X to the 1st power.
Okay. Hold on. Just 4 to 5 degree.
Yeah, that's the line y equals x, right? So that's this one.
Well, they little like bow out. You made,
Well, that
you made a
one
cool
goes
drawing.
down left as well.
It's a beautiful drawing.
What's that?
That one goes that way.
Yeah, and that one goes through.
That's right, like 2.
Yeah, exactly. You
That's
made
like
an
a-
actual drawing.
That's like a
Yes.
polar drawing. in
See this kind
Cartesian.
of funky bow?
Yeah.
So, maybe let me try to get one more on here. I'm going to try to get the idea of one on here. This is a little funky. We do x to the really big.
Next to the end.
Yeah, so x to the infinity is a weird thing. It's not quite a function. But let me do x to the million or something. So, in between 0 and 1,
They're kind of
Yeah, basically.
crawl.
it's going to be really, really small, right?
Yeah.
But it definitely goes through 0, 0.
Yeah.
It also definitely goes through 1, 1, right?
Yeah.
1 multiplied together a million times, a billion times
Still
even,
one.
it's still 1,
Yeah.
right? But it's definitely going to sit underneath of all these.
Yeah.
You guys see that? So I'm going to get this kind of,
Very.
right? It's like really basically 0 the whole way, and then it gets someplace really close to 1 and ramps way the heck up there.
Yeah.
How do I know it does that?
It's really-
Yeah. Because I know it goes through 0, 0, and 1, 1.
Because
And
anything
it's a
less than-
polynomial, right? So it's continuous specifically.
Yeah. And anything less than 1 multiplied by itself a lot of times, it's just gonna get lesser and lesser and lesser and lesser and lesser.
You guys with me on this picture?
Mhm.
Yeah.
And then on the other side, either it looks like a positive mirrored version, or it looks like a negative mirrored version, depending on
So-
whether big is even or odd.
So plugging in a big as like a variable gives you like your limit.
Yeah, really, I'm trying to get at the idea of what if you kind of took the limit, right?
Yeah, exactly.
You guys see
That's
that?
cool.
Like if you went through bigger and bigger powers, they'd kind of fold into that corner more and
Exactly.
more.
Right.
You guys cool with that?
Yeah.
Mm-hmm.
Beautiful.
Okay, cool. So this is kind of the content of section 11.6, give or take.
Cool.
Cool. So it should be noted that there are some other functions that you might want to compare.
Faster dogs. This is
Yeah, some faster dogs. So these are all the like monomial and rational power dogs, right? So
Why are we calling them dogs?
there's a theorem in calculus called the faster dog theorem.
Can you explain that?
Yeah, basically it's if the rate of growth is always bigger, right? If the dog is always faster, then that dog always gets to the end fastest.
Okay, right, that actually makes sense then. So,
Yeah, so really what I'm trying to talk about is the rate at which these things grow, right? In other words, kind of their steepness.
right.
You guys see that?
Or they all go to infinity.
Yeah, they all go to infinity, right? Like, but definitely at different rates. Like, if these are your choices for getting somewhere, right? Square roots, like the really chill, meander around, kind of don't worry about where you're getting way. The y equals x is the like, yeah, plodding along, steady pace, right? And these guys are like, go, 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 right? Like those get really, really fast.
Just not between 0 and 1.
Yeah, and not between 0 and 1, right? Between 0 and 1, their behavior is
They're
kind of
preparing their
funky.
minds for how fast they're about to go.
Got it. Yeah. Cool. It should be noted that exponential functions with bases bigger than 1 always outstrip this growth. So if you have an exponential function, it will always eventually outstrip one of these as long as the base is bigger than 1.
Mm.
Cool.
Mm.